let's make sure you've got this. So we know how to encode state, right? 22 bytes will do. If you want to do a larger encoding, go ahead. Please learn how to do it wrong. You'll learn more that way. First several times I taught this class, I let everybody do it wrong, and they learned so much. I'm such a bad teacher for giving you so much help. Very few of you are going to go do it wrong just for the learning experience. I wish you would. But yeah, if you do this, you'll save a lot of memory, and then your computer won't crash. How does one detect invalid states? So here's your puzzle. Let's suppose there is an invalid state. What does it look like?
Two blocks are overlapping.
Yeah, so I have 22 numbers, and those numbers tell where all the pieces are, but how would you know if two pieces are overlapping?
Every single piece is its own object, and they have a static set of coordinates that they occupy.
Yeah, you almost need to draw the board. Now, I've had people actually read up on graphics and draw the board like this in order to answer this question, and that's not what I mean. I mean, allocate a 10 by 10 array of bytes, right? And then set the byte, the bytes that the piece occupies. And when you find yourself setting a byte that is already set, guess what? Two pieces are on top of each other, and that means an invalid state. Does that make sense? Okay, to help you do this, in case you're struggling with it, I have visualization code. How do I know if my solution is correct? Well, this code here will actually draw this very picture. And so you can use your code and connect it to my visualizer, and you can watch it move the pieces around. And it's kind of satisfying to see a graphical program solved, right? And it will look intelligent because it is intelligent. And in fact, it's optimally intelligent. You couldn't be more intelligent than this. So if this isn't intelligent, I don't know what is in this problem domain. So if anything is incomprehensible to you, if you're having trouble knowing what your code is doing, hook it up to the visualizer. If you visualize it, you will understand your problem because that's what visualization does. And I've provided code that visualizes it for you so you can solve your problems. You don't need to ask for help. If you don't want to, you can brute force it by staying up all night visualizing and understanding and sorting out what's going on. Yeah.
Is it best to draw the black border first?
Are we doing it for the purpose of visualizing, or are we doing it for the purpose of detecting invalid states?
Detecting invalid states.
Okay. I don't think it matters. I think we want to fail as soon as possible and then return. Drawing the border will never fail.
Did you store the border just all the time, have that border, all those folks go one?
Yeah, that's what you probably want to do, is just have a copy, a template copy in memory and keep copying it. But again, this is not, I'm not judging you based on efficiency. If it just works, I'm happy. So don't get too stressed up about, did I implement the detect valid board states correctly code? Now, a lot of people have implemented it by actually checking each state. So they say, move this piece up. And then they'll iterate through the squares in the piece and check the position above it. And if it's one of the other pieces, then they'll fail out. Students that try to do it that way tends to get really twisted up in the nuances of what it means to do an invalid move. That can be done correctly, but I don't want to help you debug that because it's icky. So if you want my help, I'd really recommend you detect invalid states by just drawing the board. And by drawing the board, I mean setting an array of 10 by 10 booleans to true or false based on whether something's occupying it. And if you set something to true that's already true, you know you've occupied it twice, and then you fail out. Do something like that, and then just run through all 44 possibilities, and for each one say, is this one valid? Is this one valid? Is this one valid? Is that one valid? And then you're good. Okay? Let me show you where that plugs into the pseudocode. So here's pseudocode for it. Right here, you see where it says, for each child of the current tree process. I don't know what a tree process is, but that's the board state in which you're in. Well, for each child, You're going to check if it's in the closed set, meaning have I already seen this one before? And if you haven't, you're going to add it to the open set, meaning this is
The queue.
the queue. Yeah, that's what I meant to say. And queue. Instead of just saying for each child, what we're really going to do is we're going to say for each of the 44 possible children. And most of them are going to be stillborn, if you can forgive the bad analogy. Because most of those 44 children are bumping into, two pieces bump into each other, and you say, oh, that's not my child. Ooh, that's even worse. Okay, I'm getting away from this awful analogy. The point is, visit all 44 possible actions, and for the ones that actually produce a child, I can think of a few ways that could be a bad analogy too, then the valid child states actually get pushed into the queue, and then you'll end up searching every path but not searching any invalid paths, right? If you put an invalid state into the queue, what happens? Then it can walk through walls, and it'll find a solution really fast. Okay. What happens if you've been debugging this thing for 48 hours, your mind is numb, you just want the dang thing to work, and you just can't get it to work? What do you do? Yeah, take a nap. Okay, get help. There's a lot of things you can do. Here's the systematic, you're alone on an island with a computer, and you have to get it working by midnight answer. Stop trying to solve the hard problem and get it working with an easy problem. How can we make this problem easy? Let's set a goal of getting this blue number 9 into the top position. How do you do it? Well, you move the orange one to the left, you move the blue one up. Yes, problem solved. Woot. Right? Okay, well, that would be a lot easier to debug, wouldn't it? And while you're at it, you might as well freeze the other pieces and say moving them's not even an option. Now you know the answer. It's move the orange one left and the blue one up. You know exactly what's supposed to happen, and now you can just make that the problem and try to solve it, right? And if that's hard, make it easier. Say the goal is to move the orange piece to the left 1 square. It better find that, right? I mean, you just try each possibility. One of them's the goal, then you say, yay. Debug a simple problem. Don't debug the hard problem. Everybody that wants help comes into my office and says, Dr. Gashler, this isn't working, and we pound our heads on this really hard, complex problem. And if we just take the time to solve an easy problem first, we'd usually find the bug. And if you don't, you can ratchet up the difficulty until it is this problem, and by then you've solved it. So that's how you systematically debug hard problems, is you debug an easy problem until it is the hard problem. And so yeah, change your goal. It's not cheating. It's not the problem. It's not the assignment, but it's a nice step on the way to the assignment. So please feel free to simplify for your own benefit and then complexify before you turn it in. Yeah?
So just to clarify, when you said there were 11 layers, like it's a projector,
Uh-huh.
Are you saying that they all consider themselves at 0, 0? Or?
Yes. So imagine on these transparent overlays, there's a black dot in the top left corner, and we line up all those black dots at 0, 0, or something like that. Yeah, if you've ever played with Blender, you can move the origin of each piece around. And so we're kind of suggesting that each of these pieces has an origin at 0, 0, if that means anything to you. Okay. Yeah, and now if you look through some of this code, you'll see some useful stuff like, here I have a paint component method, and it calls shape with a bunch of stuff. Notice that my shape method takes x and y positions and calls a b, and b does a graphics.fillRect. Okay, that's a little bit nasty to look at, but here's what I'm getting at. Notice in the left, the first parameter here are the numbers 0 through 10. That's the ID of the piece number. Then I have a red, green, blue value, so I know how to draw it, what color to draw it. You don't need that. Then I have some hard-coded numbers here. What's all of that? Those are the XY positions of the squares that make up the piece relative to the location of the piece itself. In other words, if you find yourself manually staring at this picture and typing in the numbers of where all the squares in the piece are, you're doing a bunch of work that could have been saved by simply swiping them from right here. Okay, so I've done this work for you before, but maybe you'll learn something by doing it yourself, so pretend I didn't tell you that and go code it up manually. But this set of numbers right here is all of the manual labor involved in this problem besides coding it up and getting it working. Yeah?
So for the pieces, we have like the 0, 0, 0, and if you move it to the left, you would say, oh, now its horizontal position's at -1.
Uh-huh.
When we draw the board, we put in the actual coordinates of that 10 by 10 array and then just subtract 1 from it when we draw it?
Yeah, if you look at these numbers, they line up with these gray numbers I wrote in the margins here. If you think of those numbers as being added to the position of the piece, when you add them together, that's the location of where you draw it. Or it's the index into the two-dimensional array where you twiddle bits in order to see if the piece is valid, if that makes any sense. So it basically, I think I've done all the hard work for you here, but you have to take the time to understand it. If you don't understand my code, great, that's better for you. What you do is you manually get the locations of all these squares and add them to the locations of the pieces, and that'll tell you how to. Yeah, technically, if it's 150 moves, that's not the optimal answer. So what could cause that? It could be that my belief that it takes 115 moves is wrong. That would be terrible. I've done this class before. I'm pretty confident at this point. It could mean that you're not exploring one of the paths. Maybe you have an off by 1 error in visiting all the children and you're failing to check all the possible children, or your testing for invalid states is wrong and it's calling something invalid that's valid. I think those are the only things that would do it. If you systematically explore all possibilities, you should get the optimal answer. And if you can prove I'm wrong, by all means, that would be awesome, and I'll pat you on the back and all of that. Yes? Yeah, a common problem that occurs with students is they don't know how to make a deep copy of the state, so they make a shallow copy of the state. What ends up happening there? Basically, in the tree, when you move the piece over in this puzzle, it also moves the piece in all the other puzzles that have copies of it. The whole thing just gets all confused. You need to be making deep copies of your state, or you'll have a serious problem. One other bit of quick advice, use a comparator, don't use comparables. Comparables are old school, comparators are the new cool way to do it. If you use comparators, stuff will work out. Yeah.
Comparator sounds cool.
And it sounds awesomer too, yeah.
Is the starter kit a joke?
Is what?
Is the starter kit a joke? Because it's literally just like, it's just Hello World.
Oh, yeah, a whole bunch of people pointed out the starter kit has nothing in it. That's deliberate, I'm sorry. That's me being funny. But it did provide a build script for you in the format I want that shows you how to submit it. So yes, I provided nothing helpful this time. I'll provide more helpful things for future assignments. Okay, thanks for coming. See you next time.